Bonsoir à tous.
Bonsoir.
C'est un honneur pour moi de, voilà, de prendre la parole à cette occasion-là.
Power on.
Le thème d'aujourd'hui porte sur les multiverses. Or, on pourrait parler aussi d'univers parallèle, des triplés matriciels, solution de l'équation différentielle x exposant 3 plus y exposant 3 égale à z exposant 6. Et ça portera de même sur la vie dans cet univers-là. Je dis que c'est un grand honneur dans la mesure où, depuis quelques semaines, et je dirais même des mois, nous avons la satisfaction d'apprendre beaucoup sur les équations différentielles, à savoir les solutions matricielles. L'auteur aujourd'hui, c'est le professeur Joachim Mwanda, qui va nous explorer cet univers-là pour qu'on puisse apprendre davantage. Alors, professeur, nous vous donnons la parole à cette occasion.
Thank you very much. Okay, our presentation today is going to be on multiverses of matrix triple solutions of the Diophantine equation, x to the power 3 plus x to the power y to the power 6 equals to z to the power 6. And we're going to talk about life inside the universe in general. Right, so I'm going to give some outline of our talk. First of all, I'll be talking about the intro, and after that, I will give some motivation and our contribution. And the third, I'll be talking about the universe of matrix of the Diophantine equation, x to the power n plus y to the power m equal to z to the power k. I will talk about rare matrices and their properties, and also I'll be talking about matrix solutions of Diophantine equation, x to the power 3 plus y to the power 6 equal to z to the power 6 as well. And I will talk about construction structures search of matrix solutions of the Diophantine equation in general. And also I will talk about multiverses associated to the construction structure search of matrix solutions of this Diophantine equation here. I will introduce our main result. At the end, I will talk about life in general inside the universe, and then we're going to predict the non-existence of the Big Bang. Right. What we call a multiverse? A multiverse is only a collection of alternate universes that share a universal hierarchy. The idea of the existence of the multiverse have been around for a long time, but only the idea have been explored in physics theories. So that's been studied on string theory, and string theory is just the branch of physical theories, theoretical physics that's try to reconcile gravity and general relativity with quantum physics. So it was in 2018, Stephen Hawking, on his paper, A Smooth Exit from Eternal Inflation, he managed to predict that a multiverse is only a multiverse contain a finite number of universes. You cannot see any multiverse which has an infinite number of universes. So the idea of a multiverse is a little bit abstract to the most people. I think the problem is coming from the lack of understanding what the multiverse look like in terms of mathematics. So mathematicians never really spend a lot of time studying it, and that makes it be difficult to figure out what's the multiverse look like. But the idea of studying if a family of numbers which satisfy an equation, which could be the stability law of that universe, could be an interesting idea. Finding universes of matrices or numbers which can satisfy an equation, it's a very, very interesting approach. So in 2021, we did introduce a method, a way we could compute galaxies of sequences of galaxies of cross sequences of Pythagorean triples. So we managed to construct the multiverse F22C, which is only a multiverse made of Pythagorean triples of complex numbers. But what we found out, this multiverse do not have it's not like you do not have a disjoint part. So you can see this one is contained in this multiverse and so on, so on. So that gives like a limitation about the idea of multiverse. Multiverse or parallel universes is about talking about things which does not have the same boundaries, for example. So this kind of multiverse really does not give us any advantage of understanding the reality which represents a multiverse. Right. So in this study, by trying to figure out or finding all the Pythagorean triples, so we managed to create the sequences. That sequences lead us to create like a new theory, which lead to the galaxy numbers theory. It's a theory which studies only the galaxy of the universe by using numbers. Right. In 1927, George Lemaitre, he managed to prove that at the beginning, the universe was and it was like a point, a hot, dense point, and then suddenly what happened? An explosion happened, and then the universe started expanding itself until now. But that idea of the Big Bang idea is not everybody share it. The most people starting thinking about something is not right because they study the physics of the universe itself. They find out the idea of expansion a little bit it's not really clear because at the beginning it was like a small ball or small it was like a point, but what's that point where it came from? So nothing has been said about the origin of that point, who made it, where it came from, how it appeared in existence. So if it turns out that this year a Chinese physician named Ying Gu, he managed to prove that effectively the Big Bang never existed before. It's just an idea people did use to explore a little bit the universe, but that idea is not really true. Okay, I'm going to talk about the motivation and our contribution. Our work is motivated by constructing the first multiverses of metric solutions of the Diophantine equation. And also, it allows us to predict what's look like life in the universe, and also to figure out, to find out exactly the Big Bang never existed. Let's see our contribution. So our contribution, we show that this Diophantine equation here admits not only matrices from research, also matrices from research as well. So we managed to give some example of matrices which satisfy this Diophantine equation, and then we made some universe made of these solutions, and we introduced what we call the different constructions structural search of metric solutions associated to this Diophantine equation here. The construction structure search allows us to build up multiverses or parallel universes of the metric solutions is with Diophantine equation. All right. First of all, I'm going to define, I think the most people here, they know what we call by n matrices. So I'll be talking about n by n matrices and top list matrices, what it look like. So what's the n by n matrices? It's only a family of matrices which have n row and n columns, right? So what we call a two-place matrix, it's only the n by n matrix with, in which all the diagonals are constant. We give some example. For example, here we have this matrix. You can see the main diagonal. Diagonal is constant, this one as well, so on, so on, so on. So this matrix is called a two-place matrix. This one as well, you can see all the main diagonal. The main diagonal is 0, 0. And very okay, it's just constant. This is a top, it's a two-place matrix as well. And even here as well, this is another two-place matrix. Yes, constant, 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 so on, so on. Right. I'm going to define what we call a universe made of metric solutions of the generalized Diophantine equation, x to the power n plus y to the power m equals to z to the power k. Assume that we have a function defined on research here, right? The function cannot be necessarily continuous. It could be just a simple map or a simple function. So if we define research as the root of these functions, okay, or the root of the functions, going to make like a search. That search, we're going to call it like the universe of matrix triple of the positive integers here. In this first search here, every triple of positive integers is called like a planet, right? So the relationship f x y z equals 0 is called the stability law of this universe. So any family of three numbers of three positive integers which satisfy this equation is called a planet of this universe. Let me give an example. We have example 1 here. Okay, let's f m mk from n, from this search to this third one, defined this way with three numbers, positive number x, y, z. So you're going to calculate the root, the range of this triple. It's just going to be this one here. And where you can see when this function is equal to 0, that brings us to the idea of studying triple of positive integers, which satisfy this Diophantine equation here. Okay. Fermat's theorems state that in a case where n equal to m equal to k, this search is empty. It does not have any element at all for every n bigger than 3, for n equal to 3, 4, 5, so on. There is no element at all. Right, another example, f22 and 3 is just all the Pythagorean triples. That's for this one. It's well known in the literature. This family, this search is infinite. We got an infinite triples of positive integers which satisfy this equation here. Right. As I said before, f22 and 3 is called the universe of Pythagorean triples. Our recent work on finding the metric solutions of this Diophantine equation allow us to say this search is not empty at all as well. Right. Okay. We're going to get an example. We're going to fix, for example, for n. Assume that n is 3, m is the same value as k, it's 6. That means that we are required to compute all the matrix triples which satisfy this equation here. That's the idea today, and find out how big this search is, how big it is. It is small. We're going to try to figure out the size of research in a case where you have only 6 by 6 matrices. Okay, we're going to define what we call rare matrix or rare matrices, right? A rare matrix is only a topic matrix. We have a special structure which look like this one, right? We have like a constant outside the matrix, but inside the matrix you have like a constant. As the next line or the next row, you have different numbers. It could be 1, it could be any, it could be C, it could be 1, but it could be 1, it could be, if we're going to multiply C inside, you're going to see here, you got like C, 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 and then you have here C, A, which can be replaced by alpha. So you're going to have like something in the corner here, and the next row, you have different values of numbers different to this number here. Right. It could happen. We had before the first example. We had A in this side, but it could happen as well. You have the other side. So A becomes B, the other side, and then this diagonal here move to the other side. So you have two geometry. As I said, you could have RA here, and then you have this diagonal, the opposite side of the main diagonal, right? And then, or you can have this one, where it like the opposite, like the transpose, okay, so the transpose of the first matrix. In this geometry, right? This matrix is called a rare matrix of order n and index 1. Why index 1? Because there is only one element inside, which is different to the other element here, and 0. Okay, for example, this one we have if you're going to square a rare matrix of order n index 1, what are you going to find out? What's going to happen? The A in the corner here are going to move the next diagonal. You're going to have like 2. To the power, the index just specify the power of the rare matrix of order n index 1. So you can see there are 2 A here. You have 2. So the rare matrix have been introduced. We did introduce rare matrix 2 years ago, where we were doing the investigation on finding metric solutions of the Fermat matrix Diophantine equation. So as you know, since Fermat theorem been proved, we don't have any application at all. And then I didn't see in the literature any work about finding the metric version of this equation. So I thought it was like an opportunity. And then we're studying heavily. And then we discovered quite a few things. We're still exploring the equation. And we hope in the next 10 years, we will do more work and produce something very good. Okay, let's try to figure out what's look like the inverse of rare matrix of order 5, index 1. It looks like just a transpose. You transpose this matrix, but you need to take the opposite of the inverse with this number here. If it's A, you transpose this matrix, like this diagonal become this side, and this number move to the top here, and then you get the inverse. If you multiply both matrices, if you multiply them together, you're going to find E5. What's it look like the inverse of the square of the rare matrix? Well, as I said, it's look like it's a square of the inverse of the matrix. Yeah, that's what I mean. Okay. Rare matrix seems to us something very important and new and beautiful to observe. We set up ourselves some target. We want to study and the behavior of this matrix when you square it, when you calculate the power of that matrix. What does it look like? For example, if we square this matrix, what's going to happen inside? If we multiply it to the power of 3, what's going to happen to this alpha? So on, so on, so on. What will happen and how we can explore the beauty of the property of this matrix in order to solve the Diophantine equation in general. So we found out if you have a rare matrix of order n index 1, you square it, what's going to happen? The alpha in the corner here is going to move this diagonal. If you're going to cube it, so this alpha will move to this diagonal. So on, until you're going to, if you multiply this, if you're going to calculate this metric to the power of its size of its order, what's going to happen at the end, this alpha will multiply the identity. Yeah, that was happening. So it looked like, I don't know, for people who do physics, maybe they can explore this idea of moving alpha among the diagonals, what it can teach you, it can teach you something very interesting. But it's just the beginning of the work, our work. I don't know, maybe in the future people can come with a beautiful idea or inspiration to study this matrix in terms of electronic. How we're going to move this particles moving around this space or this area by changing the direction or multiplying by itself. So you got like one particle, but once you square this matrix, it becomes two particles inside. So on, so like maybe I don't do like shocks. I do really believe people who do physics or electronic, they can explore this idea and then try to design the path of alpha, and it's multiplying itself. Exactly here as well. If you going to cube this matrix, if you calculate the cube of this one, so what's going to happen? This alpha here, it was just one alpha, you're going to move until the third diagonal. You become 3 alpha. It's like a beauty, it's the beauty. From 1 alpha become 3 alpha, so on, so on, so on, so on. So what we can observe, alpha is keeping moving through the diagonals when k become big. When k is keep increasing, the number of alpha inside the matrix is keeping growing, so on, so on, so on. Rare matrices have a beautiful properties. For example, if you have a rare matrix of order n and index 1, if you're going to calculate this matrix A alpha to the power n, what you're going to find out, you're going to end up with you're going to have alpha multiplied by EIN, the identity of n by the suite of n by n matrices. Okay, we're going to calculate in practice some solutions of this Diophantine equation here. Okay, let's find out matrices of order 6. So as you know, our studies focus on studying the property of rare matrices. This gives us really a lot of advantages for constructing or finding the geometry, the proper geometry, which can fit inside this Diophantine equation. Right. A alpha, the geometry of A alpha allows us to construct metric solutions of this Diophantine equation. First of all, if we observe the property of this matrix is a rare matrix of order 6 of index 1. What does that mean? If we're going to calculate A alpha to the power 6, you're going to have A alpha multiplied by EI6, which is only the identity element of the suite of 6 by 6 matrices. Okay, from here, we can 6 can be what 6 look like. Just 6 is the same as 2 times 3, right? It's the same. 2 times 3. Okay, if we have A beta to the power 6, we know it is which one, okay? But what about if we replace alpha or beta by the sum of alpha plus beta? We're going to have exactly the same alpha plus beta multiplied by E6. And then it becomes easy. If we're going to add this one to this one, it's going to, if we're going to add this element to this term to this term, you're going to have this one. It gives you alpha plus beta multiplied by I6, which is only what would look like if we go back to the property of real matrix of order 6 index 1, is only this one plus beta to the power 6. So what that tells us, this equations tells us a square alpha, yeah, and a beta, a alpha plus beta, this triple is only a metric solution of this Diophantine equation. In other words, we can say this sequence here, this sequence is only a sequence of planets of this universe. It's very basic, it's not difficult, very easy to calculate. If you know, if you have a computer, you can check it as well. Right. So finally, we're going to see F A alpha, which is on the geometry we did use to construct solutions, is a universe. But that universe is only a part. It's only a part of this universe. It's like a small part. It's not all the universe. Just a small part. Because we could change the geometry of A alpha, we could choose different construction structure to build a research as well. So research is very huge. We're going to guess exactly how many elements we can find inside. I don't know if we can be able to figure out all the part of research. Probably not, but we can guess, at least, or maybe the minimum. Right. As you can see, A alpha is the geometry of the metric solutions of the Diophantine equation. The geometry is called the construction structure. So in order to calculate this solution, you need to use the geometry of these three matrices, this triple here. Like, as you know, A alpha is not the only unique geometry which can allow us to construct the solution of this Diophantine equation. Exactly, we have quite a few. We have quite a few geometry. We could use A alpha transpose as well, the geometry of A alpha transpose, and then it can allow us as well to find new metric solutions as well. For example, we could replace A alpha by A alpha transpose. Exactly, if we use this triple as well, we're going to be able to figure out metric solutions of this Diophantine equation here. So finally, how many geometry we have? We have quite a few. We have 1, 2, 3, 4, 5, and also we have here 5, 6, 7, 8. We have 8 construction structures of metric solutions of this Diophantine equation. That means we have exactly 8 geometry, which could allow us to construct different solutions. Right. As you can see, every construction structure, that means every geometry here, allows us to construct an infinite number of metric solutions of this Diophantine equation. For example, as I said before, we could use this this geometry here, A alpha, A alpha transpose to get this one, right? Exactly this one as well. It's a new family, it's a new sequence of metric solutions of the same Diophantine equation. But as you can see, this universe is completely different from the other universe we had before. This universe is completely different to this universe. They're all different. They don't have any element between them. They are completely different and separate. Right. Finally, A alpha itself allows us to generate at least 8 universes, which are infinite. Each universe is infinite. Does have an infinite number of elements. The big question is, if we manage to construct the metric solutions of this Diophantine equation by using 6x6 matrices, could we found another dimension, another size of a family of matrices which satisfy this equation? Well, let's try with 3x3 matrices. Let's try. But it seems that this equation here does admit different families with different sizes of matrices. For example, you could get 3x3 matrices or 6K by 6K matrices. Let's try to construct the first 3x3 matrices, which is satisfy this Diophantine equation. As we know, it could be probably there are many geometry which could allow us to construct these solutions, but we just found one, like red matrix of order 3 of index 1. As well, if we calculate, right, it's very easy. If you're going to calculate this metric to the power 3, you're going to have alpha multiplied by I3. I3 is the identity element of the set of 3x3 matrices. If you square it, you're going to have alpha square, right? You're going to have alpha square. That's going to be, if you square this one to multiply by the power to the power 3, you're going to have beta. If you square it, you're going to have beta square. It's the same here. If you multiply, if you're going to calculate this to the power 3, you're going to have delta plus b to the power 2 square. For this one, if you're going to calculate this matrix to the power 3, that gives you 2 delta beta plus delta square. Right? It's very easy, very, very trivial, not very difficult. Right. What's going to happen if you start moving alpha? If we change alpha amongst all the columns of this matrix, we're going to have different matrices. For example, if we're going to move this alpha here, we get this one here. This matrix is different to this matrix. What will happen if we move this alpha here? You will get this matrix. All of these three matrices are completely different. So this search is called the search of construction structures generated by the matrix, this matrix here. The search of construction structures generated by A alpha 1. So it's just the family of matrices is going to obtain by moving the first element of the first column amongst the other columns. I don't know if you understand what I mean. Right. So we have here, for example, if we get the transpose of each matrix, you're going to find out research has exactly 6 elements, right? And that could allow us to construct in each of them. So P alpha is inside here, Q alpha is inside here, H alpha as well is inside here. So that's mean how many way we can choose P alpha 6 times. P alpha could be any the 6 element inside. Q alpha as well could be any element inside this search. So we have how many choices you have exactly you're going to get. Okay, back. Yes. So it look like you're going to be 6 times 6 times 6, which give you 36 multiplied by 6. You're going to have probably 200 something universes. So we said we managed to calculate matrices by using only a 6 by 6 matrix. We managed to construct a universe, and then now we have another family of a universe of 3 by 3 matrix. So we have like two different sizes which satisfy this Diophantine equation. That's a very beautiful property. Having one equation, and then you have 2 groups of elements, of 2 groups of matrices, square matrices, which satisfy that equation. That's very, very interesting. Right. So let's find out what's going to happen if we're going to consider the construction structure search of the 6 by 6 matrix. So we as I said, we still using the same family as rare matrix order of order 6, right? And next one. So what we're going to do here, if we move alpha, the second column, we got this one, and third column, we come this one, so on, so on, so on. We're going to have exactly 6 elements. If you're going to put all these elements with the transpose inside one search, we're going to have a search here, and where we can see in a case where you have 6 by 6 matrix, this constructor structure search has exactly 12 elements. As you can see, this search is another family of it's another constructor structure of the matrix solution of this side of this Diophantine equation here. Right, we're going to calculate the constructor structure of search of matrix solutions of the Diophantine equation in general. So we're going to assume A alpha is a rare matrix of order, and the next one, and then we know it's easy to calculate the element of the geometry generated by that matrix. So A alpha J will indicate the column where alpha need to be. For example, if you have 1, alpha going to be the first column. If you have 2, alpha will move to the second column, so on, so on, so on, so on, so on, so on, until you get at the end. Finally, you're going to find out research here is going to have exactly 2n element research. Okay, we're going to talk about the multiverse or multiverses associated to the construction structure search of the metric solution of this Diophantine equation. Okay, as I said, this Diophantine equation has an infinite number of constructed structure search of different sizes. In particular, you have matrices for research M6K with entries positive integers. As I said before, a multiverse is just a collection, it's a collection of alternate universes that share the same universal hierarchy. We know it's easy, for example, here to construct research here. We already know it. And then we are able at the moment to calculate the first multiverse of 6 by 6 matrices. If we're going to choose K equal 1, so we already know this one. We know this set has 12 elements, and then if we want to, so this look like this set got like 12 geometry, and then from this 12 geometry we can figure out how many universes we can construct, how many separated universes we can construct. Exactly, we have P, we can choose P alpha 12 times. We can choose Q alpha 12 times. And we can choose H alpha 12 times as well. So we have look like 12 multiplied by itself, that gives us 1,728 universes inside here. So that's massive. Each universe is infinite. Right. Now we can introduce our main result. Our main result says that there exists an infinite number of multiverses of matrix triple solutions of the Diophantine equation containing each a finite number of universes of matrix triples. How do we show that? First of all, we're going to track all the 6K by 6K matrices. Okay, assume that K is 1. We already said it before. We know we're going to choose a rare matrix of order 6 and x1, this one here. And then what we can do, we know by the geometry of this search, we know this search, this construction structure search has 12 matrices, 12 geometry. And then from that observation, we can choose to calculate one of the universe. This one, as you know, P alpha, there are 12 matrices. P alpha can be chosen between the 12 here. It's the same as well, the same idea. And finally, you got the same conclusion you had before, which is this is the number. The first, the multiverse of order 1, which has 6 by 6 matrices, has exactly 1,728 separate universes. Each of them is infinite. Each universe is infinite. Okay, let's increase the size of the matrix. Assume that K is 2. What's going to happen? So we're going to have matrices of order 12, and the next one just look like this matrix here. As you know, it's very straightforward. CS2 of this one going to have 24 matrices, 24 geometry. What that tells us, we are able to construct this universe P alpha. You have 24 way of choosing P alpha, Q alpha, H alpha. We end up with this one here. This search is infinite. It does not have a finite number. You have an infinite number of matrices, of matrix triples here. That look like sequences, really, if you see them, because delta, beta is moving around here. So this look like a sequence, really. Okay, so we're going to say the multiverse of order 2, which has 12 by 12 matrices, has got inside 24 multiplied by 24 multiplied by 24. That gives us 13,824 universes. So the more you're going to increase the dimension or the size of the metric solutions, you're going to find out the universe has more universes. So the size implies an increased number of the universes inside the multiverse. So you can guess what's going to happen for K sufficiently large. So you're going to have you end up having a multiverse. You have an infinite number of universes. That will happen. So that let me improve what Stephen Hawking says. Every multiverse has only a finite number of multiverses. We know the most if K is finite, you will get a multiverse which has a finite number of universes. In the case K become like very large, infinite. So that's multiverse. The associated multiverse is going to have probably very close an infinite number of universes. What's happening? We're at the wrong place, I think. All right. Okay. Okay. So the same way we can construct the search of the geometry, the constructing structures. We know every A alpha satisfy this equation here, verify this equation, and then it's easy for us to calculate this search here, which is the KEM construction structure search of metric solutions of this Diophantine equation. This Diophantine equation here, if we modify the element here, we are able to generate the Diophantine equation we're studying. So if we're just going to multiply 2 by 3, and then we're going to bring 3 outside, this is look like the equation we're studying here. And then you have this one, this one, this one. We can, it follows that this equation here allow us to say this triple of metric solutions satisfy this Diophantine equation. In other words, we can say that this universe here, made up of this sequence of metric triple, is infinite as well. It's an infinite set. This is because you got like the terms of a sequence, an infinite sequence, which has an infinite number of terms. And there you can see the KM multiverse here. It has got exactly 12 multiplied by 12K multiplied by 12K, which gives us 1,728 multiplied by K cube universes. Thus, give us the desired result. So now we know every matrix for every finite K has a finite number of of multiverses. Each one is an infinite set. I mean, got an infinite number of terms. Okay, so let's bring this idea in real life. What does that look like? So let's study a little bit the universe. What's look like life in the universe? What's look like life on Earth first? And then we're going to extend the idea by similarity, what's happened in the universe, inside the universe. As we said, assume that we're going to consider this Diophantine equation as the life equation. I mean, for example, every triple of matrix which satisfy this equation will be called a living creature, right? For example, the heat. The heat. Do you know every living creature has got some heat on it? Plants got heat inside of them. You got some heat inside of you. All the animals, even inside the sea, or fish, they got heat inside of them, right? Every living creature got the heat inside. So that means the heat is shared by many kind of living creatures. Okay, another equation. This Diophantine equation can be considered like love. You know love? You love. Everybody on earth got love. You can love. So everybody got love are part of the universe with this Diophantine equation as the stability law, right? So a Diophantine equation can be considered as heat or as a stability law, like there are many stability like hate. Hate can be a stability law, and when everybody got hate, you can put them inside the universe of hate. So the universe of people who share hate like a stability law, right? So a Diophantine equation gives us many opportunities that allow us to explore the unknown, the things we never know, we never knew before. For example, um, um, the existence of a multiverse. This is the first time we figure out a family of universes made of mathematics equation. Right. We say this Diophantine equation has an infinite numbers of sizes of matrices. So you have matrices of order 3, 6, 12, so on. It never finish. Right. If we're going to assume this equation as the life equation, we're going to say every triple of metric solution with the different equation as a living creatures, we will go to end up say there exists or there are an infinite number of living creatures inside the universe. Right. If this one represents the life equation, right? So due to the fact that this equation admits an infinite number of different sizes of matrices, we're going to say life equation. So there are an infinite number of living creatures. Okay, that idea allows us to predict life inside the universe look like. As I said, our main result says this Diophantine equation has matrices of this family, which is satisfied this equation with no boundaries. There's no bond. There's no limit. So the I mean, in terms of sizes, we don't have any boundary. We got the smallest size of the matrix, which is satisfy the matrix which satisfy this equation, where we don't have the final size or the bound of the final matrices, which is satisfy this equation. We do not have it. As you can see, it looks like an increases sequences. This one keep increases in terms of sizes, so it's getting bigger. That means so there are creatures, living creatures, which have a very massive size. So you have matrices, big matrices and small matrices. Okay. So the Earth is bounded. The Earth got some limit. We even have the diameter. We can calculate the circumference of. We can calculate how the Earth is big. And then we say there are an infinite number of living creatures. The Earth being bounded, we cannot have an infinite number of visible. Let me say visible. Maybe it could be an infinite number of invisible living creatures, but let me say an infinite number visible creatures. In terms of visible creatures, we do not have an infinite number of living creatures. So, I mean, living creatures can be considered like plants, animals, insects, right? That are all living creatures. Or the creature can die, who can eat and get sick. That's a living creatures. A stone is not a living creatures. The stone, the sound is not a living creatures. I mean, for example, a tree, a mango tree, or any fish, animal, they are all living creatures. Right. So, due to the fact the Earth is bounded, and there are an infinite number of living creatures, therefore, there are other living creatures which lives not on Earth, the other planets. Yes, other planets. They're not on Earth. They live in other planets. Well, for example, on Earth, we have plants, human, fish, animal, bird, viruses. We all share the life equation, life as an equation, right? But outside our universe, outside our Earth, there are other living creatures very far away from Earth, which have a very, maybe the double of its Earth in terms of size. If you look yourself, our solar system, you're going to find out the sun is very massive. Jupiter is bigger than our Earth. So on. So the more you go away, the planet you get there is bigger than the planet we got here. But we have our limitation. Our technology got a limitation where everything is based on observation, right? We cannot technically figure out the other planet what they look like unless if we can be able to produce different telescope can go there and then study it. But the Diophantine equation allows us to predict, even we don't have any equipment, we can predict what's happening elsewhere in other planet. What's happening in other planet? If we observe our planet, you're going to find out the sun. The sun got the heat. Every living creature's got the heat. Our Earth, in the middle of the Earth, there is a heat. You got the heat. Fish got the heat. Plant got the heat. Everybody got the heat. So heat generate life. Where there is a heat, there is life. Where there's no heat, there's no life. So if we observe the Milky Way, you're going to find out there are many suns. Each sun is a living creature. It has been said, our sun will die one day. Our sun is not behaving as it used to. On the surface of the sun, there are explosions. What does that tell us? Our sun is dying. So if the sun is dying, it's just a living creature. In other words, we're going to say even our earth is a living creature. This earth is a living creature. This earth, we can make the earth happy. We can stress the earth. We can force the earth to die if we destroy the ozone, if we destroy our atmosphere, if we continue polluting the atmosphere. What's going to happen? This earth will die younger. In other words, our earth needs some extra care, as plants need extra care. If we want to exchange a good relationship with plants, with the earth, we need to take care about the earth. Even the sun, it could be probably the things we do here could disturb other planets. So in the universe, the sun, planets, galaxy, planet system share love as an equation. It's not a secret anymore. You can search on Google or whatever. You're going to learn there are sun are born every day in the universe. There are explosions. There are sun are dying. Some planets are dying. Some other galaxies are dying. The other galaxies are born. So it's not something new. But what we need to remind ourselves, life is not about only Earth. Planets live, suns live, the universe lives. If you look yourself, inside of you, you got cells. Cells, they got the heat as well, they live. So our planet, the Earth, inside the universe, is look like only a cell. So the universe itself is a living creature too, which does not have a beginning and the end. So finally, life in the universe is very complex. It's shared by invisible and visible living creatures. In terms of invisible creatures, for those who have some faith in God, it's very easy for them to understand what's happening. But if you don't believe in God at all, it's very difficult for you to understand even what I'm saying now. For example, people say angels lives. Angels, people have seen angels. People did meet angels. They met them. Maybe you already met an angel, I don't know. Or people say about evil spirit, bad spirit. People say about that. So it's something even our ancestors, they know about this. If you go in your village, right? If you go to celebrate like a marriage or a visit, you're going to find out the chief of the village will get like someone who will talk, and then you will talk to people who were dead before. For him, people who died, people who already passed away, they never disappear. They are somewhere. So the problem we're going through is the lack of understanding, the lack of getting deeply what's most important, what life is for, who is a living creature, which relationship we can build up between living creatures. We are all connected. We are connected each other, human to human, human to plant, human to the earth, human to the sun. So if we don't know all this knowledge, well, we're still going to be ignorant on earth and nothing will happen. So that leads us to conclusion. We have like the universe proposal. We always say what we think, what we predict. The universe is only an infinite dimensional metric solution of a Diophantine equation, where galaxies are entries. Therefore, the universe do not expand. The universe has the behavior of a matrix. A matrix never changes size. each entrecôte is on place. That's the universe. The universe is vast. The planet. If you modify the distance between the sun and the earth, something will happen. If you modify the distance between the sun and our the moon, something will happen. So it's unshakable. You cannot change it. So it has been fixed like that because the distance between them has a relationship. So you cannot modify it. So the Big Bang never existed. That point, the hot point never existed. It cannot be the beginning. So the universe has been designed by something never, which does not have a beginning and an end. So you heard about, so the universe is just a giant living creature which have no beginning and end. Right, I'm going to finish here. So, and that's the end of my presentation. Right.
OK. Merci bien, professeur Mwanda, pour cet exposé. On ne va pas faire de grandes transitions. On va passer à la deuxième phase de questionnement et de compréhension accentuée. Alors, s'il y a des préoccupations, des questions, je pense que c'est l'occasion de poser ces questions-là qui vont être l'objet de discussions et d'échanges. Alors, pour les questions, nous sommes dans la phase de questionnement et d'échange. Alors, est-ce qu'il y a des questions, soit pour éclaircissement ou bien pour approfondissement? Est-ce qu'il y a des questions?
Oui, bonsoir, professeur.
Et bonsoir, Maï.
Oui, d'abord, avant tout, je voulais dire merci et félicitations au professeur Monda pour ce brillant exposé.
Thank you.
Et merci pour ce qu'il apporte encore dans les mathématiques à l'humanité. Je voulais un éclaircissement par rapport au univers parallèle.
Right.
Par rapport au univers parallèle où il a considéré les alpha, bêta.
OK. Alpha, beta.
Descendez. Les structures de construction, là, en bas encore. Plus bas. Voilà, ici. C'est ici, là.
Right.
L'ensemble FP, P alpha, Q alpha, H alpha.
Okay. So P. So you mean here? Yeah. Right. So P alpha is just a geometry. Right. Q alpha is the geometry inside research, as well H alpha is the geometry of research. What's look like Q alpha if you go back? Is this family here? And this element, we already know them. The matrices is this form, right? Or this matrix form. And then we're going to use this geometry to construct a solution. So if you inside here, P alpha is not the solution, it's the geometry you use to construct this one. In order to get this one, you need to know P alpha first. And then once you know P alpha, you're going to be able to calculate P delta. Yes? And that will allow you, if you want to square it to the power 2k, that will help you to figure out the solution of this Diophantine equation. It's the same here. Q alpha is not the solution, is a geometry we use to construct Q beta, right? It's the same H alpha as well. And then this is the solution. Here are just the geometry. The real solution are these numbers, which are triple of matrices. Does it make sense?
Mm-hmm.
Right. Okay.
And en bas, plus bas, recette MK.
NK.
MK.
MK. Yes, yes, yeah. This is the multiverse of order K, right? So because you have a
K multiverse of solution. Pourquoi c'est
this is the multiverse which has 6k by 6k matrices. When k is equals 2, it's going to be 12 by 12 matrices, the size of the element of this matrix. If k is equal to 1, you're going to have 6 by 6, right? So k here indicate the size multiplied by 6 of the matrix inside this set. It doesn't make sense?
I understand. Thank you, Professor.
Oh, thank you.
Alors, on va continuer dans l'élan des échanges, des questionnements. Est-ce qu'il y a d'autres questions? Est-ce qu'il y a des questions?
Pas une question, hein, mais sinon souhaiter joyeux anniversaire au professeur Mwanda.
Very much. Thank you. Happy birthday.
Okay.
You're getting old, you know.
Happy birthday to you.
Mais en tout cas, joyeux anniversaire à vous, hein, professeur.
thank you very
On
much.
n'avait pas cette
Je
information-là.
vous envoie une bouteille de champagne, toi et Stan.
Thank you. Thank you very much.
Thank you, Dr. Raoult.
Birthday, Professor.
Okay. Alors, je voulais juste intervenir un tout petit peu. Ce n'est pas une question véritable, mais ce qui me fascine, en fait, à la base, c'est que pour l'équation x exposant 3 plus y exposant 6 égale à z exposant 6, on n'a pas eu recours à la matrice carrée de 3. Et ce qui est fascinant, c'est que c'est une petite matrice et qui sert à construire une famille de solutions matricielles. Et ça, c'est vraiment surprenant.
C'est comme le plus petit microbe, quoi. En fait,
Voilà. Cette seule matrice,
il doit exister la plus petite particule doit exister. Alors, ça nous enseigne que la plus petite particule doit exister.
C'est-à-dire qu'on pourrait s'attendre à que pour une telle équation, on va considérer voilà, trois matrices qui n'ont pas à la base la même structure géométrique. Mais c'est juste une matrice là qui, par endroit, est déformée et qui permet d'obtenir une famille des suites finies des suites d'ailleurs infinies de solutions. Et ça, c'est vraiment assez remarquable. Je voulais faire une là-dessus.
Yeah, maybe we don't know. Probably you can get 5 by 5 matrix which satisfy this Diophantine equation. We don't know. It could be because we still have quite a few work to do finding this metric solution, but we don't have all of them all at the moment. But I think working more, probably going to get maybe 5 by 5 matrices. We don't know, or 4 by 4 matrices. We don't know.
Okay.
Yeah. Hello, Dr. Sam, you don't have any question?
No, I'm still checking what you have done.
S'il y a des questions, des remarques, c'est l'occasion de, voilà, d'en parler. Alors, je vais continuer pour dire que jusque là, ça me trottine, en tout cas, après d'avoir suivi plusieurs exposés sur les équations différentielles, le problème de solution matricielle. J'avoue que rien que pour les équations pour lesquelles les exposants sont de petite taille, il met à ce stade encore difficile d'avoir une matrice qui est remplie, je veux dire au niveau des cellules, où il n'y a pas un grand nombre de zéros, de trous, et qui permet aussi de construire une famille de solutions. Et je n'arrive pas à comprendre à quel niveau se trouve la difficulté, quoi. Et ça, c'est assez surprenant. Parce que les matrices rares, là, elles sont quand même assez, voilà, elles sont assez aérées compte tenu des cellules qui contiennent que un grand nombre de zéros. Voilà.
Right. Yeah, it's still a subject of study. So, as I said, we don't know yet all the geometry. But what you sure we're going to continue working on this direction, make it a little bit more rich by using different sizes or different geometry. And I hope we're going to find a matrix which has less zero inside. But as you know, matrices, they got a different behave as numbers. They don't behave the same. And it's more difficult to manipulate matrices than numbers. Numbers are quite more easy. If a number is less than 1, if you square it, you get a number smaller than 1. But matrix does not behave like that. You see, so it's about finding new geometry, right? That will be challenging because we don't have technically we don't have any program or any computer. It can allow us to design new matrices with new properties. That can be done only if we fully engage ourselves by studying it.
No, they are. Actually, they are.
Maybe
yeah, they are.
we
There
try
are
to
new tools which I think moving forward we will study them
all
and
right.
see how they work and how they're gonna make our job much
Yes. So
help us
yes,
to come up with new structures
new structure with less zero.
Yeah.
Right.
Yes.
So probably
they are.
probably I would need you to show me how to get that because we need to find a new geometry. So we find out the geometry where alpha can be factorized by the product of positive integers. But what about if we found a matrix with less zeros inside it? Inside what's going to look like? Probably we could find something, but it's still complex. It's not an easy idea. But at least we found one structure which allows us to construct the solutions. But it's not a bad idea finding new other structures as well. Yeah, well, that's good.
Ouais, mais ça reste une piste de réflexion, hein, trouver une telle matrice qui est assez, avec des
But I
cellules
think
qui sont occupées.
moving forward, we just exploring a few tools. But I think we're gonna move into artificial intelligence,
Yeah.
generative one. Uh, uh, this is a
Only one.
generative technology. It's not it's not I would say cognitive artificial intelligence. But I've explored a few tools. Today I was hoping to finish with them, but I haven't. I was working more to find things for little children, how they could come to work with it without being overwhelmed. So it's there are tools, and I've seen a few of them. So now I need to go through them and try to sift through these numbers because they are today more than 25,000 tools of
Yeah.
artificial intelligence of anything you could think of at the moment.
I think what I'm just guessing, if you got the matrix with less zeros inside, so you're going to have inside the matrix like things like square, a square, or a to the power 4, something like that. That's going to limit when you're going to add them together, you're going to have inside the matrix, for example, a square add r cube add r square, something like that. That will complicate the issue. But I think we need to start thinking about tracking different geometry. Yes, different geometry. But at least this is not an easy object, right? Finding metric solutions of a Diophantine equation is not easy at all. So it seems easy for us, but it's not easy to manipulate, you know. So even if I'm going to use, for example, a rare matrix of order 100 or 1,000, you can see we got to struggle how to with what we're going to use to find it. But at least by our work, we know by using the properties of a rare matrix, we can just guess. We can find the conclusion. But if you have to calculate with your hand, that could be challenging. See what I mean? Yes. It's still a difficult subject. Finding metric solutions of a Diophantine equation. It's not easy at all so far.
No, but this is why I say there are few tools, Math GPT being one of them,
Right.
where it's not cheating, but actually it's working because things like Julius AI and other, which
Right.
kind of allow us to resolve mathematical problem, is
Right.
to try to give them. We need to try to postulate something, and
Right.
then from that, once we postulate, we work together with
Right.
the solution
Right.
to see what it can uncover.
Okay.
And then we manually can go and verify because they're not cognitive, i.e., they are generative, i.e.,
Yeah.
it means they are prone to mistakes. So we cannot rely solely on the result.
Right.
We have them to go manually,
Yes.
verify
Verified.
what
Yes.
they have found, and
Right.
then ensure the properties which it told us it has actually meet the geometry which we are trying to uncover. If it
Right.
doesn't, then at that point we just turn around and say, okay, because many of these tools sometimes, and I've done with many of them, where actually when you verify the answer, you realize no, they're wrong. It's not the right answer.
Right. Yeah. Yes. 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 I think it probably GeoAlgebra does it somewhere. So when you're going to calculate the root of a function, it gives you numbers, confusing numbers. Right. It's
But it's a lot of them because they're not cognitive yet. They're more generative. Therefore, they are prone to make few mistakes in their deduction because they are deducting. They're not. They're not. Uh, they're not intelligent to think by themselves.
Right. Okay, that's good. Okay.
Ok. Bon, mais il y a aussi un autre aspect. C'est quand je regarde d'une certaine façon, c'est à se demander est-ce que ces matrices-là, qui sont solutions, du point de vue de la réduction des matrices-là, hein, est-ce on peut espérer qu'elles aient une, une valeur propre commune ou bien enfin, un vecteur propre commun?
Yes, I think as I said before, I think what we're planning to do is to study a little bit each geometry. For example, if every matrix which satisfies the Diophantine equation, if you're going to calculate the eigenvalues, what does it look like? Is it to share something in common? So that's an opportunity. You see, that's another way of if anyone can get involved of studying maybe the eigenvalues or the characteristic function generated by this matrix, that would be good. But what's most important is the geometry first. And then each matrix we can study, for example, this is like a linear bounding operator, this one. So we can find out if this linear bounding operator is polynomially bounding or it's powerly bounded or it's power bounded. So there are quite a few things to study. Well, so far I didn't think about studying about the eigenvalues case, but that's another opportunity. Try to study different eigenvalues of this matrix inside the construct structure search. What's look like the eigenvalue for each matrix? We have seen, for example, this one has 6 elements. What's going to look like the eigenvalues of the research? That would be an interesting subject to study, right? Maybe they share a common value we don't know, but studying that direction will be good.
Ok, merci bien, professeur. Est-ce qu'il y a des questions, des préoccupations, des éclaircissements? Est-ce qu'il y a des questions? Alors moi, je réitère mes remerciements au professeur, hein. Voilà, c'est l'occasion de le dire ici. J'ai appris beaucoup de choses dans le cadre de cette théorie-là et je pense que je vais encore apprendre.